Good morning, everyone. Welcome back to the automation webinar of the SESAR. Most of you will probably have been listening in on last Wednesday already. For those that are new, I'm going to redo the introduction at a slightly higher speed. Since the COVID lockdown, we have been expanding our efforts on reaching out through webinars. So we've already done a couple of webinars on use space and drones, on exploratory research. Various projects presented themselves, nurturing young talent, the Digital Sky podcast about the COVID-19 impact, recovery measures, resilience in general, and ATM. And this series that you're looking into now is about the Digital Academy webinars, which are focusing on industrial research. It started off on the 30th of June with the presentation of the European ATM masterplan. Last Wednesday, we had the first session on automation. Today, we have the second. Then we will still have a couple of more after the summer break on use space results, communication, navigation, and surveillance, virtualization, trajectory-based operations, SESAR, and the environment. So all the webinars are recorded, and those that have been done already, you can find on the SESAR website. I think I didn't show that here. If you go to the SESAR website on the news and events, past events, you'll see all the recordings. The ones of Wednesday is not yet online, but it will be online very soon. A little introduction on the levels of automation and moving towards higher level of automation. If you look in the ATM master plan, you'll find this diagram, which shows that we're moving from very low level of automation to full automation with full autonomy, with a question mark how far we will get in the end. Here you see the phases of the ATM master plan, and we're discussing how far we can push this, and that actually has two aspects to it. So one is which tasks can be automated, and how far do you want to go with that in terms of information acquisition, information analysis, decision and action selection, and action implementation. The other part is about the type of automation, and we're in particular looking in the context of this automation webinar on artificial intelligence, machine learning, big data. Last Wednesday, we had already the general introduction. So starting with an example from NETS on time-based separation during approach using big data, then a general introduction about different waves of machine learning, artificial intelligence. We had a presentation from IMHOTEP on the human-machine hybrid approach, how we see things going to work together in the human and machine environments in a collaborative way. And the certification and safety assessment perspective from EASA, trustworthiness and artificial intelligence. So with that general and kind of theoretical framework as a background, we're now moving today to more practical examples. We have two examples that are still under research. The first one is on big data analytics to study intermodal passenger behavior from Ricardo Herranz, the first speaker from Nomen. The second one is machine learning and speech recognition, which was in exploratory research, has moved on to industrial research, which will be presented by Hartmut Helpke from DLR and Anita Serna from the air navigation service provider of the Czech Republic. Then we move on to two applications which are already running in operations, again, using what's called here deep neural networks and machine learning in two projects that have been collaborating as they were running. One from Maastricht Area Control Center presented by Cedric Belcora, and one from Eurocontrol presented by Ramon Dalmo Codina. There is an opportunity for asking questions, which has to be done online. If you look on the right side of your screen, you see, well, the first one is the chat, but the second one is the questions. So in the chat, you can write whatever you want, but as speakers, we will be ignoring that. If you have any questions that you would like the speakers to answer, then please ask them in the questions tab. The speakers will try to answer them online while the other presentations are ongoing, but there is also some time at the end for questions and answers, which we'll do in the panel discussion. And with that, I hand over to the first speaker. Ricardo, the floor is yours.
Okay, so screen sharing. Oops. Okay, so good morning, everyone. Thanks to the SEAU for the invitation to present our work here in this webinar today. I'm gonna try to provide you with a quick overview on what we've been doing for the past few years in the field of big data analytics applied to the study of passenger behavior, and how we can hopefully use this information and the insights we can extract from a number of big data or new big data sources to let's say enable a better integration between air transport and other transportation modes. I am Ricardo Herranz. I am the co-founder and CEO of Nomon, which is a small technology company based in Madrid. We're a small team, around 30 people. And we're specialized in the provision of information, analysis, and decision support tools for the planning and management of transportation systems. And we've been particularly active in the SESAR exploratory research since the beginning of the program. And one of the areas in which we have focused our research is precisely the analysis of travel behavior and the use of new big data sources for the analysis of how passengers interact with the air transportation system. I think we would all agree that when assessing any kind of investment in new transport infrastructure or transport technology, etc., we need both information, both the supply side and the demand side. And I think it's quite well known, I would say, as of today, that the transport supply information has improved a lot in the past few years. We have digitalization of travel schedules, we have online travel planners, we have, in general, very good, very detailed information on transportation supply. And the big unknown in most projects, that the big gap is usually on the demand side, on the behavior of travel demand. Traditionally, the tools we have used to characterize travel behavior have been mostly based on travel surveys, different types of travel surveys, which are expensive and which are time-consuming. I think we are all more or less familiar with household travel surveys or passenger surveys performed at most big airports, and they have a number of well-known limitations. We typically collect samples that are smaller than what we would want to. The quality of information is not always as good as we would like because of issues with respondents, willingness to answer certain questions, etc. Information becomes outdated very often, and it's usually not fully adapted to all the problems we want to tackle with this information. So for many years, what we have done in the field of transportation engineering is to develop a lot of theory to, let's say, to fill these gaps or to update the information we collected from travel surveys. We have now a number of opportunities to, let's say, overcome or at least mitigate some of these problems. We have a number of technologies that we can broadly classify into two major groups. First, we have different types of mobile devices attached to persons or attached to vehicles that provide information on people or vehicles' trajectories, such as mobile phones, smart cards, GPS navigators, etc. And then we also have a number of sensorization technologies, such as cameras or different types of traffic counts or people counts that provide, let's say, a more static view of flows at one point of the network. All these new big data sources share a number of properties. They are geolocated. They enable passive data collection without the intervention of the traveler, of the user, and in that sense, they are, so to say, objective data. And most importantly, they are longitudinal data. We are moving from data sources that we could call cross-sectional, such as surveys that are performed maybe once every year or once every 5 years, depending on the type of survey, to data streams that are available every year, every month, every day, almost every second, I would say, right? So this opens a number of opportunities in transportation planning. So basically, we have, I mean, if we have to summarize the properties or the characteristics that make these new big data sources interesting, I have simplified it into two main items. First, we have much bigger samples. We will see several examples along these presentations. Samples such as data from mobile phone operators provide us with samples of maybe 20, 30, 40% of the population, as opposed to a survey in which we are maybe interviewing 1 or 2% of our population. And this allows a better segmentation of travel demand. And then I already mentioned this, we have longitudinal data, and this opens the door to the observation of a richer variety of travel behaviors and opens the door to observing behaviors that change in time scales that are shorter and shorter and that are not observables with other, let's say, observation instruments that let's say peak data every year or every few years, right? So this is something that has developed in transportation along the past decade. It's not something new. We've been working in this field for several years now, and the question is, what about aviation? How can we adapt these technologies or make sense of these technologies in the particular context of the air transport system? So let me take a step back here. I think we are all familiar with the high-level easy policy documents that advocate a so-called passenger-centric air transport system, which is thoroughly or seamlessly integrated with all transport modes and takes travelers from door to door in a predictable and efficient way. And I think we've been hearing this mantra for several years by now. But I think we have to admit that so far air transport operations have not put probably sufficient emphasis on the passenger. And we argue that one of the reasons for this is that research in this area has traditionally been constrained by the limited availability of passenger behavior data. We have traditionally relied on similar data sources as in other fields of transportation. We have travel surveys or passenger surveys. We have statistics or public statistics published by organizations like Eurostat or more specific air transport organizations like Eurocontrol. And we also have a number of aviation passenger intelligence solutions made available by providers like IATA, for example. And the question now is, how can we take advantage of all these new opportunities, these new, we could call it passenger-centric data sources attached to devices that are let's say, centered in the passenger, like mobile phones, to complement or to overcome some of the limitations of these traditional sources. Basically, when we started thinking about this around 5 years ago, the question we posed to ourselves was basically this one. We are seeing that these big data sources are being exploited successfully in other areas of transportation. What are the specific opportunities in the field of air transport? How can we use different types of data coming from smart personal devices to combine them with more traditional data sources and extract improved insights about passenger behavior and hopefully inform decision-making processes in air transport in general and in ATM in particular. And it is with this purpose that we launched this project 5 years ago, Big Data for ATM. It was a SESAR exploratory research project funded in the first call for exploratory research projects. It started in 2016, if I remember well, and ran for 2 years. And was a project led by Nomon with 4 other partners, IFISC in Spain, Fraunhofer in Germany, the Hebrew University of Jerusalem, and ISDEFE, also in Spain. And basically what we were trying to do in this project was to explore the potential of different types of new big data sources to characterize different stages of the passenger door-to-door journey. We looked at a wide variety of data sources in the project. We looked at data from mobile phone operators. We looked at data from social networks, data from public transport smart cards to characterize the access and egress legs. We looked at other types of data coming from airport sensors to characterize the behavior of the passenger within the airport. We don't have time in this presentation to go through all of them, so I will focus on giving you a quick snapshot of the work we did with mobile phone records, which was one of the data sources with which we worked the most in this project. For you to understand very quickly what we are talking about when I say mobile phone records, we worked with a data set shared for the purpose of this project by Orange Spain, formed by anonymized records that basically register or consisted in the interactions of every mobile phone network, every mobile phone, sorry, connected to the Orange network. Every time it interacts with the network, because you perform a call using an SMS, you update a data session, or there is some sort of update in the network, this registers an event, which is later on used for billing purposes or for network management purposes, and basically provides a sample of the spatio-temporal trajectory of every user in the network. Right? We had data for Orange clients and data also for roamers that connect to Orange network. So this is very interesting because we also had data for foreign visitors that travel to Spain in this case. In total, the sample was around 26-27% of the total Spanish population. Right? And this is a short video that shows you how this raw data would look like if we looked at every individual register one by one. We see something like this, right? You see in the bottom right corner, you see the time of the day. So let's wait until this starts again. So okay, we're now during the night time, right? It's midnight now. Early in the morning, we will start to see some registers here. This is someone probably living in the city of Valladolid, north of Madrid. At some point in the morning, it takes the road to the Madrid airport. It disappears at the airport. It appears half an hour later at Barcelona airport and visits some areas within the city. What is it interesting, or why is it so interesting about this data? And why is it, we think, complementary to other data sources we've been traditionally using in the aviation domain? What is interesting is that we get the whole door-to-door multimodal chain in this data. We see that this person has traveled by road to the airport. We see, by the way, that he or she avoids the toll road and takes the non-paying road. So this is telling us something probably about his willingness to pay, the kind of passenger we are analyzing. Then it takes the plane, and we can investigate what are the places that this person is visiting later on in Barcelona, right? So basically, without going into the nuts and bolts of all these, because it's a rather sophisticated process, but to summarize the way we analyze this data, it consists mainly of five main steps. There's a pre-processing and data cleansing step, where we get rid, let's say, of incorrect registers or corrupted data, etc. Then we select a sample of users. We need to find let's say, a good compromise between quality and quantity of data, and pick users for which we can, let's say, reliably assess their activity travel patterns. Then the core of the technological solution is the activity trip detection module that you can see here, where we convert what you've seen in the previous slide into a set of activities and trips between these activities and different stages or different legs composing these trips. Then we expand the sample of users to the total population of travelers by blending this data with other types of social demographic statistics like census or total number of passengers per airport, etc. And we finally aggregate this data to preserve privacy, of course. Everything we produce is in this project, and in general in any project where we work with this data is aggregated and fully anonymous data, such as origin destination matrices, travel times, etc. Some examples of what we did in the Big Data for ATM project, things we were able to measure with this data. For example, we analyzed the Madrid-Barcelona, Madrid-Catalonia corridor, analyzing the modal share between air transport, high-speed rail, and road. So we can see in which areas, which origin destination pairs are dominated by air transport or by high-speed rail or by road. We can analyze airport catchment areas in a very precise and fine-grained manner. Here we can see the graph is probably not very nice, but I think it's very enlightening in the sense that it shows very well what we can do with this data. If you look at the at the pictures on the right, this is the difference between the number of high-speed train trips originated in every area and the number of air transport trips. So we can see basically blue is negative. It means that we have more air transport, or that air transport has a higher modal share than rail, and the orange and red dots are those areas where rail has a higher modal share. And this is, I think it's very interesting. Actually, this is something we already knew, but we can now quantify it. In the areas around the Madrid airport here or the Barcelona airport, air transport, of course, is the dominant mode. When we move to the city centers, high-speed rail gains market share. So this is telling us that accessibility to airports or high-speed rail stations, intermodality matters in the choice of the long-distance transport mode. Something we measured also in this project were door-to-door travel times. We have a single data source that is allowing us to follow passengers from their origin to the final destination. So we can split the duration of the trips into the duration of the different legs. We can measure, for example, how much time passengers spend at the origin airport, how much time it takes for them to access the airport, how much time they spent at the destination airport, and finally, how much they spend in reaching their final destination. These are some results. For a small experiment we did in the project, analyzing all the trips, all the air transport trips traveling from anywhere in Spain to the Madrid Barajas airport, and analyzing how the total door-to-door travel time is split between the different stages or the different legs of the trip. And what we can also do with this data is to analyze or to quantify these behaviors for different types of airports or different types of passengers. Here we were comparing, for example, the what we were calling here curb to gate time, or the time spent at the origin airport, for different types of airport in Spain. Typically, we see that this is shorter for business airports like Vigo or Barcelona, where we have a higher proportion of business travelers, and this is longer for what we could call touristic airports like Malaga or the Canary Islands or the Balearic Islands, where people are typically traveling with family, children, baggage, etc. Right? So we have an observation tool that is really allowing us to characterize the behavior of different types of passengers. After this big data for ATM project, we've continued this research in other projects. So this is a line that has been quite successful for us, and that has given rise to a number of new initiatives. I will give you just a few examples. This is a project we did in collaboration with AENA here in Madrid, trying to blend the information extracted from mobile phone records with the information they get from annual passenger surveys. What we did here was using the surveys to characterize a subsample, let's say, or a small sample of passengers, and look at the behavioral patterns of business passengers, leisure passengers, etc. And then we use those patterns obtained with the survey to implement algorithms that found those patterns in the mobile phone records, such as duration of the stay at the destination, departure date, return date, etc. And we use this to segment the behavior of passengers according to the purpose of the trip. This is another project in Spain for our Ministry of Transport. This is a much more ambitious project where we analyzed all interurban trips in Spain for a couple of months, analyzing the modal split for all medium distance and long distance corridors in Spain, so we can see which are the relationships or the interprovince relationships in this case that dominate long distance travel behavior in Spain, and how different city pairs are configured in terms of modal share. And this is the last example. This is a very recent project which is actually ongoing now. It will last still for a few months. We are working also with our Ministry of Transport, monitoring mobility in Spain on a daily basis. We started a few months before the start of the COVID-19 crisis, and the project will monitor the behavior in the next few months to analyze changes in mobility patterns along the crisis, to monitor the effectiveness of confinement measurements, and to try to derive information that help epidemiologists analyze how mobility is influencing the propagation of the disease. Right? So to conclude, I think this gives a very general overview of what can be done with this data. Where are we now, and where are we going in the near future? I think it is clear now, after a few years of research in this area, that the data streams generated by smart personal devices offer a huge potential for improving the way we understand, we model, and we forecast the behavior of transportation systems. We have data on passenger behavior with a level of detail we never had before. But there are also a number of challenges we need to face when dealing with this data, which are in general common to many big data sources. These are noisy data, these are often biased data. They were not collected for the purpose we are using them for, so they often have less explanatory power than traditional data sources like surveys. We need to infer things that were directly observable in a survey. And finally, there are also some other types of challenges that I haven't discussed in the presentation, which were more focused on the technical side, but there are also regulatory, organizational, business challenges, such as those linked, for example, to privacy protection, algorithmic transparency, etc. I think in terms of conclusions, we can say that we have all these new data sources, mobile phones, smart cards, etc. But as of today, none of them provides the full picture. So there is a clear need for data fusion techniques. There's a huge benefit in blending this data, this external data or this third-party data, we could say, with more specific air transport or airport-based data, such as, for example, data from airport sensors. Algorithms matter. I try to present the whole thing in a very simple way, but small details in these algorithms make sometimes big differences in the outcome. And for this reason, I think validation experiments and rigorous evaluation experiments that allow us to test the accuracy of the information we extract from this data is essential to gain credibility and to get this integrated into normal business processes, right? So as a conclusion from this big data for ATM project, we identify a number of research threads to continue with this line in the future. And basically this has led to two new SESAR exploratory research projects that have started, one of them a couple of months ago and the other one month ago, which are Transit and IMHOTEP. And this is the end of my presentation. I will quickly present what each project is about and how we intend to take further what we did in big data for ATM. And hopefully I think this can be a good basis for discussion later on in the debate session. The first project, Transit, is trying to take advantage of this data to build a long-distance travel model at the country level. We have two case studies, one in France and one in Spain, where we are modeling all long-distance trips in the country for several months. So we are using this data first to characterize the behavior of long-distance travelers in Spain, in the case of the Spanish pilot, and calibrate a transport model. And then we will use this model to evaluate the impact of a number of intermodal transport solutions based on enhanced information sharing between air transportation and other transportation modes. So basically the idea here is, okay, if we enable a better or higher levels of information sharing between air transport and ground transport modes, what can we gain or how much can we gain in terms of reducing door-to-door travel times, in terms of improving travel time reliability, in terms of promoting more sustainable modal choices. So this is a project focusing, let's say, on the strategic evaluation of intermodal concepts. The second one, IMHOTEP, is a project also conducted in collaboration with some airports. We have two case studies, in this case, the London City Airport and Palma Airport in the Balearic Islands. And the focus here is on real-time decision-making, unlike the previous project, which had a more, so to say, strategic focus. Here we are looking at how to use this data in real time to make better management decisions, right? Transit is probably more focused on the planning dimension. Here we're looking at the real-time management. How can we use this a combination of historical data on passenger behavior with real-time data on what is happening at the moment at the airport and in the access and egress modes? And how can we use this to to build a short-term forecast of the behavior of the passenger flows, what time different types of passengers are arriving in the airport, how much time it will take for them to go through the different sub-processes, etc., and how can we make sense of this information to make better decisions, both from the point of view of the airport management, for example, allocating more or less resources to security checks or checking counters or whatever bottleneck we have along this process, but also on the ground transport side, how the fact of having better information about air transport delays, about the types of passengers that are arriving in an airport at a particular moment can help us improve the connection between the airport and other transport modes and design, let's say, a better tailored offer for those types of passengers. These are the ideas we are exploring now. If you want more information, I put in the last slide of the presentation a number of links that I think will help you dig deeper into these topics. And nothing else from my side, I think. Thanks again for your attention, and we'll be happy to discuss any questions at the end of the session. Thank you very much.
Thank you very much, Ricardo. That was a very elaborate and interesting presentation on passenger behavior study. Also interesting to see that there are already there's actually even commercial interest for this kind of application. So it's not just exploratory research, but it's actually already being implemented in practice. I did see already in the questions, but also in the chat, I saw some concerns raised on GDPR, privacy, and on data ownership, and maybe also data reliability. I don't want you to answer it now because you already ran over time a bit, but maybe you can start thinking about that, because we'll probably come back on that question in the discussion later on.
Sure, I'll try to reply on the chat, and then we'll discuss it at the end if you want. Yeah, sure.
Thank you, Ricardo. Hartmut Helmke and Anita Serna, could you please come on stage for the next presentation on speech recognition?
Can you confirm that I'm on stage already?
Yes, you are. Sorry, see that. Anita as well. Go ahead.
Okay, can you see my screen?
Yes, we
then
see it.
No, it's in the presentation mode. Yeah, then thank you again for everybody and the opportunity to speak to more than 170 people here at the moment. And I try the impossible to press our speech recognition projects during the last 8 years into 15 minutes. So I try that to do together. I'm talking about the speech recognition part in air traffic management, and my colleague Aneta will then afterwards talk about an application we had together with Thales in Rungis. Okay, if you're talking about speech recognition, well, what we mean with this? Well, we are always starting from the utterance of ATCOs or pilots, and then we have something like a voice-to-text block, which transforms the utterance into a sequence of words. Yeah, something like Turkish 5 Kilo Juliet, reduce 220 knots, descend 3,000 feet. But yeah, to be honest, that's the easy part. What people are really interested in is the more challenging part. We need the semantics. Now we need to extract the call sign from that it was reduced, and that was 220 knots, or the values. And well, we were quite successful during the last years with that at DLR, though we used for that what we called assistant-based speech recognition, because we use an assistant system to support the speech recognizer. That means we are using the weather data, the radar data, and so on, to predict a set of commands which the controller might say in the current situation. Yeah, with that, we really were able to reduce the error rate and to increase the recognition performance. Yeah, and at the end, well, of course, you have an application, for example, showing the recognized 3,000 feet value in the radar display. Now, that's a challenge of speech recognition. Of course, there are other applications than just filling the radar labels, for example, just highlighting the call site, keyword spotting, that means, for example, recognizing go around, integrating also with CPL DSC, of course, workload prediction, or I think the King's discipline at the moment is really readback error detection, though where you have to recognize also the noisy pilots. Now, what is needed for speech recognition? Yeah, as already Ricardo also said, we need data, and we need also data. Yeah, and why we need all this data? Well, you need all the voice utterances and their transcription, though what is said, just to understand how different accents or different speakers using different accents are pronouncing some words. So to develop really different acoustic models. Well, and at the end, you also need the semantics, because what is written in the book, how the controllers should say that, or yeah, that's just a theory. At the end, well, experienced controllers have a different interpretation, though, and if you want to be taken serious, you need to also recognize those controllers. Therefore, you need all the data. And well, here you have to the data privacy issues. The transcription is very expensive, and even more expensive is the annotation, because well, some years ago the rules were even missing to interpret the semantics. I come back to that. Yeah, we started that in 2013 and 14 for Düsseldorf approach area, where a group of experts developed a speech recognizer with really 95% of recognition performance already on command level. But it was a little bit expensive. Yeah, and we started therefore the Mallorca project ending in 2018, where we tried to just use all the data from the radar and from the voice recordings of the controllers. And by machine learning, we created from a baseline architecture a speech recognizer for Prague and for Vienna. So we replaced the expert just by machine learning. And the invention of Mallorca was here using not annotated data, just their automatic transcriptions for learning. Well, that's state of the art for a long time in speech recognition. Right? You have the voice data, have a speech recognizer, and you try to learn from that. The invention of Mallorca was now to also use the radar data to predict what might be possible. And with that, you can, with some probability, to classify all the automatic things into good data and into bad data. And then you know if you're learning from bad or from good data. And you should also learn from bad data. Yeah, that helps. And well, we validated that. Well, we used data from August 2016. We add and we learn from them. We got a speech recognizer August version. Well, we take all the measurements, for example, the command recognition rates. We added then data from September, got the rates, added data from October, got the rates, added data from November, got the rates. Well, and of course, what we expected is such a learning curve that with more data, we get increased performance. Yeah, and that indeed really happens. Here you see the learning curve for Vienna with our baseline architecture. Without additional data, we just had 60% and ended up at 85%. For Prague recognition rates, well, we started with 80% and we could even achieve with 100% means 23 hours of data just. We ended with 92% of recognition performance. Yeah, the challenges of the Mallorca project were really the transcriptions. Yeah, for example, the controller says just follow the A320. How are you transcribing that? Is it just by words follow the A320, or are you writing the numbers, or is it a capital A? Yeah, so at the end we agreed on the red one, but that are the challenges. Yeah, you need to agree on something. And that we did in the 1604 project, which ended last year. That we developed with 22 partners from 15 European countries, and so-called ontology rules for transcription and also for the annotation part, the semantics of controller utterances. Yeah, for the utterances, for example, the challenge is, if you have, for example, Speedbird 861, resume on navigation, proceed direct to rapid. Yeah, what is the meaning of that? Yeah, okay, the meaning is clear. Yeah, but how do you write it down? The call sign in that way, a direct with a blank, and then to, maybe the word waypoint to rapid, navigation on, or are you repeating the call sign with an underscore? Yeah, all these things, yeah, need to be agreed that you can share data between different speech recognizers, and that you even can exchange different blocks for speech recognition. Yeah, that you get more data, because yeah, the data is the expensive part. And that we just did in the 1604 project. We agreed here on the common ontology for the semantics. Anita, may I hand over to you that you give a overview on the trials we had in Thales?
Thank you, Hartmut, and good morning to everybody from Prague. My part is focused on a personal view on voice recognition and machine learning, as ANS Czech Republic contributed to exploratory research Mallorca, and a follow-up one, PJ 1604. First mentioned one was quite far from ops room, but on the other hand, it clearly shows our interest in bringing a voice in ops room, and the main driver specifically for us was also the fact that we are going to replace our main ATC system soon, and we know, and it was already seen in other countries, that if it's not fed by data on time and complete data, we are losing some fancy functionalities of the system, and the support of the system is not so good as it could be. Sure, our controllers are here, they can enter a lot of data in there, but in high traffic scenarios, they cannot do that, and this is the problem we are seeing. So on Wednesday, I think it was Mr. Baumgartner who mentioned automation and integration system in his very interesting presentation. And yes, we are using this to improve the situation. And despite the fact that the ATC domain is quite conservative, we are also seeking more innovative and autonomous solutions. And ASR is one of that. Hartmut, next slide, please. So let's talk about voice recognition in ATM domain. This is not the first time we see voice recognition in there, because a very good example could be ATC training, replacing pseudopilots, monitoring stress or ATC workload. So we know it's there, but how to use it in operational room, and we go even farther. We want to use it directly in a radar screen of the controller on tactical base. So this slide shows typical interfaces to voice recognition system that can be seen in ATM, and Hartmut already touched those interfaces, but I would like to touch machine learning and voice recognition as such from our perspective. Maybe I cannot say too much as a description. I would rather ask several questions. So first one, how does it fit to this standard structure of system supervision based on regular checks and calibration? Or how are we going to approach to learning assurance that was also mentioned by Elsa on Wednesday? And so there's a lot of questions, and at the end I would ask, is voice recognition and machine learning really black box from our perspective, or we are going to approach it in different manner? Next slide, Hartmut, please. So let's move to the PJ 1604, which was highly motivated by very good result presented by Hartmut from Mallorca. And another second point was that industry partner was also in there. This was where we moved to the lab with real TMA, Prague TMA environment, and the main goal was to have some automatic inputs to the labels regarding the clearances, and also automatic highlight of control aircraft. Comparing to Mallorca, we should say that the machine learning was not included in this validation, and another thing is that there was no acoustic model for Czech English dialect. So what we achieved actually in a PJ 1604. Next slide, please, Hartmut. Yeah, so if we are moving quickly to the result, on the left side you can see recognition rate per specific command groups. If you look on the numbers, we are somewhere between 0 and 82%, and it differs really significantly. But we should not forget that specific command groups are also important to the controllers in different way. For example, altitude commands are something that they are really requesting, and we can compare it to something else which is not so needed for the operations in fact. On the right side, there is recognition rate per ATCO, and you can see that one controller, and it was as expected, had a really good result. Another one maybe a little bit lower, but there is one common observation for all scenarios. And then if we go from first run to second run, the recognition rate improved regardless the traffic load. The fact that maybe it was the reason that the controller tend to stick to the phraseology because they saw that voice recognition support them, so they really started to think that okay, phraseology is good and the recognition rate improves. And the last comment that I would like to mention on this slide, and I ask Hartmut to click on, is that we should not forget that error rate is something that our controllers are really sensitive. So if you look in this error rate type distribution, you see that about 10% we had incorrect value when the correct aircraft was highlighted. So those are the errors that the controller needs to correct it, and it's time consuming, and ATC workload is not on good level. Wrong aircraft highlighted, yes, it was about 2-3%, and nothing displayed, which is not a serious problem, was about 11%. And last slide, Hartmut, please. Comparing to Mallorca, I would say the results were not so good as it could be, and comparing the results from Mallorca, but our controllers had the overall perception which proves that ASR, operational feasibility and performance, is really at good level, which is nice output from this validation. And in Czech ANS, we really decided that we want to go further and we want to monitor what's new. And there are a lot of interesting facts that I could mention here, but I don't have so much time. The most interesting one would be that if we really improve the acoustic model, we can get even better recognition rate. And if a controller improve the pronunciation, they can also get support from ASR, which brings a higher recognition rate. I think that that's all for now, and thank you, and give the floor to Hartmut again.
Thank you, Aneta. Yeah, and I have a last slide. Aneta had the last slide, though this is the roadmap, just to show where we started with speech recognition in the SESAR environment and where we want to go. That's based on a slide created by Ruben Flor in 2017 at the Mallorca intermediate meeting. So we started with the ECLISTEN project, which was done by DLR and Saarland University. We had recognition performance already for Düsseldorf for 95%. We continued 1 year later just for quantifying the benefits of speech recognition. And here we could show that with speech recognition to comparing no speech recognizer, we could really reduce fuel consumption per aircraft by 60 liters of kerosene, or we could enable 2 aircrafts more per hour as landing rate. Well, we continued that in the Mallorca project, where we adapted to Prague and Vienna here in the machine learning framework already. Our error rates were there 0.6%, and for Vienna 3.2% on command level already. And well, we continued here in the 1604 framework, and these are 2, wave 1, where we developed the ontology, and we make this validation trials, with Aneta has just talked about. We also, in that same, we for the first time concentrated on prediction of commands in the tower, to be precise, in the remote tower environment. And where are we going now? Well, an approach of clean sky, together with Beauty, Brno University, EDIAP, Saarland University, is to concentrate on transcription on flight level 24 data. Another project in wave 2 is solution 97, where we really for the first time want to develop speech recognition for the tower environment. And in the framework of solution 96 of wave 2, we really want to go to the ops room of Vienna, where we at least want to show the results to the supervisor. And well, one of the most interesting projects is Hawaii, which might be, as the name already suggests, a follow-up of Mallorca, standing for highly automatic air traffic controller workstation with artificial intelligence integration. I learned long for saying that words. And here we really want to concentrate on the King's discipline of readback error detection for pilots. Yeah, we really want to recognize the pilots, and not just for small airports. We have concentrated now on one of the interesting and complex areas in Europe for the London TMA. And of course, also the Brexit will be a challenge for that. Yeah, though I hope that in 2 years, Ruben, you invite me again to present something successful about that project. But yeah, that's my dream. Thank you very much for your attention.
Thank you very much, Hartmut and Anita. Again, very interesting projects that I've followed over the last years, and I think it also makes an interesting link to the discussion or the debate between how long do we still need voice versus when are we going to make a transition towards data link. It also has an interesting link to another topic that I've been following over the last year, which is related to SWIM, System-Wide Information Management. So the more data that is automatically recognized through speech recognition, both from controllers and pilots, the richer the whole system will be, and we'll be able to share that through SWIM with other operational actors. So that enables, again, to improve the whole system, to optimize the system further. Let's go on with the next presentation from Cedric Belcoura from Maastricht's Upper Area Control Center. The floor is yours.
All right, thank you. So I'm going to show you a little bit the little things that we do in machine learning to handle the complexity in our day-to-day workload in MUAC, in Maastricht. All right, so the first project, I want to focus on the trajectory prediction improvement. So what you see in the screen here is called the IFMP. It's a tool that the controllers that is used in the ops room, and basically what it does is that it shows you a forecast of the occupancy counts per sector for the next 6 hours. Okay, so all of these bars here are the occupancy expected at different sector, depending on sectorization, depending on the time also. So of course, the more away you look in time, the more uncertainty you have. All right. The thing is, we can separate this uncertainty in 2 parts. The first one would be a time uncertainty. Aircraft have delays, etc. And this counts actually, part of these bars will move left and right. Okay. And Ramon in the next presentation will show how we can tackle this problem. I will focus, or in MUAC, we have focused on the other side where the bars actually move up and down. Why does that happen? Well, it happens that controllers have a very strong, let's say, tendency to give direct to flight. And that is very good for the environment, very good for the passenger, for the airline, awful for the guys that use IFMP to handle the upcoming traffic. So we needed a little bit to tackle this uncertainty. Okay, so the goal here is by improving the trajectory prediction to determine, to let's say correct these uncertainty on the vertical axis. So actually, we already had a first version implemented in 2018 for the east-southwest flow. This is a machine learning algorithm that basically predicts the route that will be taken by the flight, probably as long as 6 hours before the flight actually happens. We have included in December 4 new flows after ATCO validation session. And now we cover more or less 15 to 20% of the traffic. Why did we add only 4 new flows, and why we only have 15% of the traffic? Well, it appears that even if you have a perfect prediction, that doesn't mean that you would have the correct sector sequence for that flight. And remember that here we are interested in improving the sector countings. So I can give you an example. Look at this flow. You can see in black, this is the flight plan. In blue and red, these are the prediction. And you can see that both prediction and the flown trajectory crosses this sector, which never happens, never assumes the responsibility for that flight. So indeed, the controllers have some working habits. They skip sectors, they bypass ones, they try maybe sometimes to respect more what the flight plan was about. There are several reasons behind it, but this is the main reason why we cannot, let's say, expand it directly to the full traffic. And this is very important. The problem here is that the trajectory prediction, you can actually measure the accuracy of the prediction by comparing the predicted route to the flown one. So you have 50% improvement. You can also measure the improvement in nautical miles, whatever, but you don't have a direct assessment of what is the effect on the sector countings, because what you can measure is the geographically crossed sector sequence, but the assumed one is actually very different. And this is why we have the second version now that has 2 complementary algorithms. The first one will be implemented in September 2020 and is basically an extension of the version 1 with the vertical profile included. And we have, very importantly, a second algorithm that will be implemented in early 21 that will allow to extend TPI to all flows. How? Because it will take the geographically crossed sector and will tell you which ones will be skipped. All right, so it will, let's say, match it to the sector that will actually assume that flight, so the real sector sequence of interest. Some important notes here that I think are necessary. The first thing is that this tool that we are building is reactive to military activation changes. And this is something that was not happening before, and is very important for the day-to-day use. If you can see here, the flight plan in dot, and the flown and the prediction go around the military restricted area. What happens when that area is not active anymore? Well, the flight plan does not move, but the flown and the predictions take the shortcut and actually end up crossing a different sector. So you can see here the obvious benefits in terms of sector countings that this improvement brings. Another important note is about validation and monitoring. As I said before, if we had only the trajectories, yes, you can measure that your trajectory is closer to what really happened, but you cannot determine if this improved the sector sequence. So we had to add this second algorithm to make us validate or monitor at least the behavior of our pipeline, or let's say of our input, in an automated way, without having to request every time an ATCO session when you can go through the data and ask them whether they think it will be good or not for the sector counting. So this, we have it covered. Now we can validate, we can monitor in an automated way, and this is very important for pursuing any type of project. Another very important point is the stationarity. So one thing is that the day of tomorrow, we can have new agreements between MUAC and neighboring sectors that changes the way we deal with flights. If we would base everything on machine learning, that means that we would have to wait for data to accumulate and train again the models to include these new rules. And this is not very reactive. So how can we deal with that? the thing that we did basically is to keep the deterministic hard-coded logic that we have in-house. So basically, if there is a new rule, you just integrate it as the other rules are already integrated, and you have it directly working on your pipeline. So basically, this leads to a cascaded implementation. If you look at this, we receive the flight plans from NM. We have firstly a hard-coded logics that are implemented for the route transformation, and then only we apply the ML-based algorithm. Then from these, let's say, ML trajectory, you apply again the hard-coded logics that we have for the sector crossing extraction, and only then we apply the ML-based sector cleansing, let's say, to determine which one will be skipped. And finally, the final output is displayed in the IFMP tool for the controllers to have less uncertainty on their data. All right, I can go on much more on this, but I think that it's also interesting to show you other things that we are developing currently at MUAC based on machine learning. The thing that I want to show you is something difficult to quantify, let's say, to explain. It's called complexity projects. And basically, we want to understand what is the complexity of given situations. The thing is that if you think about it, imagine that you would have a perfect flight trajectory, perfect prediction of the trajectory that the flight will have. Then really you wouldn't be able to detect a lot of problems, because ATCO already decomplexified everything to handle their traffic. So really the notion here is you're not really needing a prediction of a trajectory, not one. You actually need several scenarios. What can happen with that flight? So let's say that we are here noticing a shift in paradigm. We passed from predicting one trajectory to predicting probabilistic trajectories. So if you look here in the graph, you'd see that in dotted again the flight plan and in green the flown trajectory are both enveloped in a red area. This red area is basically what we call the probabilistic trajectory. So you can understand that the less certain you are about what your flight will do, the wider this area will be, and the more certain, the narrower it will be. Okay, and we actually expanded this to the vertical profile also, which is good. So how do we use that? All right, we have a probabilistic trajectory, but it's nothing in itself. How do you use it to transfer it to complexity, to something that measures complexity? Well, never mind the equation, focus on the idea. We want actually to try to measure the interaction probability of a flight. And how we will do that? You select a time t, so in 5 minutes, and actually the probabilistic trajectory gives you an area where the flights might be, and for each of the points of this area, a probability to be there. And that for all the flights that you have at that snapshot time. So what you can do is sample, following the probabilistic distribution, the positions of all the flights, and compute how many of these positions break some ruling distances. So for example, 10 nautical miles and also on the vertical level. And from that, you could actually extract a value or two values, let's say, about each flight. First, the interaction probability. So 100% would mean that if the flight behaves the way you do, or given, let's say, the uncertainty that you have on that flight, you have 100% certainty that you will interact with at least one flight. And the second information that we can extract is the number of flights that it might be interacting with. Okay, So maybe imagine a flight that will start descending, and you have 3 or 4 flights crossing perpendicularly. So this is one flight that will probably interact with 4 flights. And this is very important. We will show you later. Why do we want that? Well, basically, if we were able to identify complexity, there are multiple opportunities that open. First, basic classification between basic and complex flights. Maybe the basic flights can be handled somewhere with different protocol than the complex ones. We can also assess the sector complexity with some look ahead, maybe 20 minutes ahead, and the controllers or the ops room might handle this situation differently. The same can be said for clusters. An agglomeration of situations that might be problematic, and we can take measures ahead of time to decomplexify it. All right. So now the thing is even more, let's say that we are entering a little bit more deeper into this. Okay, we have the interaction probability, we have the number of flights, but is it really what the controllers consider complex? How can we assess that? So actually what we have done, this is the first experiment that we have done, and I will explain a second one. The first one has been done with a reduced number of controllers, so only 3 controllers that were close with us. We have created some snapshots for different sectors and a visualization tool where they can play around with. And basically we have asked them, without them knowing what the complexity measure that we have is, we ask them to give us an output. So to look at the situation and to give us the complexity that they felt. All right? And then what we did is take the interaction probability per flight, the number of flights, and try to find out a function that will help us fit that the values of the controller. Is it exponential according to the probability, or logarithmic, or just linear? This type of simple fitting. What I can show you here is a first very encouraging results. First thing that you should notice is that it's indeed overall increasing. So the value of the complexity that we have fitted is indeed increasing with the feeling that the controller had, which is perfect for us. But there are a lot of artifacts, a lot of wrong classification, and etc. Well, we have looked with details on these situations to determine from where they come. Well, firstly, we have determined one flow of the experiment, because the look ahead here were too high, and then the controllers were moving along time, and then let's say that their assessment is based on a different time than the algorithm. So we have actually changed this experiment. We have created a new one, and it will be now assessed by more than 60 controllers for 400 snapshots, and hopefully we will have a much better fit after that. The other type of, we have looked more also into details, but the situation where the algorithm and the controller were not agreeing, and more, I mean, overall, the controller, let's say, return on what our complexity was saying, because it can actually highlight which are the flights that are involved in this complexity. Very encouraging and very nice. So there might be some technical filtering, some technical things that we need to add to fit it more, but this is based on only 1 or 2 outgoes. We don't want to overfit too much. So that's why now we have, let's say, started this second experiment phase, and hopefully at the end of it, we will be able to show you much more precise analysis. All right, thank you all. Happy to answer any questions.
Thank you very much, Sadek. Very interesting presentation. The next one is very close to this, feeding actually into improving these predictions for Maastricht Upper Area Control Center. Cedric, just for your awareness, I halfway your presentation encouraged the audience to ask some questions because we didn't get a lot of questions. Now we're overrun with questions, but if you could have a look at that and start thinking about which ones are interesting enough for the panel discussion afterwards, and start answering the rest. Meanwhile, also for Anita and Hartmut, there are a couple of questions on voice recognition as well that you may want to have a look at. Ramon Codina, the floor is yours.
Yeah, I am just trying to share the app window, but I see that I have some issues. So, okay. So I will share this. So can you see the slides?
Yes, we see it.
Yes, excellent. So first of all, I would like to thank you for attending to this webinar, and also SESAR for inviting me. It's a big pleasure for me to present the results of this project that we did in collaboration with MUAC, and that is highly related to what Cedric just presented before. So MUAC is using machine learning to improve the trajectory predictions, and Cedric showed that they are improving both lateral and vertical predictions. But at the end, the trajectory of an aircraft is a sequence of 40 points. So latitude, longitude, altitude, and also time, meaning that any deviation in time could be as important as a deviation in the lateral route or in the altitude profile. Because obviously, it is important to know where the aircraft will be, but also when the aircraft will be there, in order to compute accurate traffic demand figures in terms of entry counts and occupancy counts. Because if we consider, for instance, an aircraft flying at 500 knots, an uncertainty in the entry time of 15 minutes, which we will see that is typical, results in an uncertainty in the along path distance of 125 nautical miles, which means that the aircraft could be at any sector of our airspace in reality.
Ramon, sorry to interrupt you. I'm still on your introductory slide. Are you actually, is that correct?
Yeah,
is that just the title still? Okay.
Yeah, it's correct.
Okay.
And most of this time deviation comes from the takeoff uncertainty at the departure airport. And this is what I am going to explain right now, how to improve the takeoff predictions with machine learning. So I will start by a very illustrative example of the problem that we want to address. The enhanced traffic flow management system collects data from multitude of sources like ANSPs, airspace users, airports, etc., and also distributes data that can be used to compute the demand. Okay, let's imagine that we have a flight that sends the initial flight plan at 6, and according to this initial flight plan, the aircraft has an estimated takeoff time of 9:15. For a given flight, we may receive several messages from the initial flight plan to the actual takeoff. Okay, so we might receive several updates, updating, for instance, the lateral route, the requested flight level, and also the estimated takeoff time. In this example, this flight sends another periodic transmission at 8, which modifies the estimated takeoff time to 15 minutes before the initial estimated takeoff time. With this example, I want to show that for a given flight, there might be more than one estimated takeoff time, because the estimated takeoff time may change from the initial flight plan to the actual takeoff. But then time goes and the aircraft takes off at 9:45 because it's delayed for several reasons. This means that the error of the ETFMS system, the prediction error, at 8, okay, at 1 hour before the estimated takeoff time, was 45 minutes. We believe that some of these prediction errors of the current system are systematic, and that if we use the right features, so if we extract the right information and we use the right models, and we train these models with a lot of historical data, we could learn the systematic errors and improve the predictions of the takeoff times. So the idea is, okay, let's try to, so this is how the distribution of takeoff time errors look like. And the idea was, let's try to extract some information from the data that we receive okay, in the ETFMS from this data. And this will be the input features to the model. And the machine learning model that we will train with hundreds, thousands, even millions of examples will be able to predict, given the conditions, so given the inputs, the features, the prediction error of the ETFMS system. For instance, in this example, the model receives some data, some features, and predicts that for these given conditions, the system typically underestimates the takeoff time by 50 minutes. So then we can simply correct the takeoff time according to the ETFMS, and hopefully obtain a better prediction with the machine learning model. So this is the idea, not to predict the takeoff time itself, but the error of the system, given the input features. So I will start by presenting the features that we fit to the model in order to predict the takeoff time error, and also the models and the results. I must say that all this information was published last year in the SESAR Innovation Days. So if you want more information, you can download for free the paper in the website of the conference. Okay. So for instance, in this example, the machine learning model gives a better prediction than the ETFMS. So the features can be classified. So these are the inputs to the machine learning model in order to make the prediction in several categories. In the first category, we have the features that are directly related to the flight, like the departure airport, the destination airport, the airline. Also, this one is very important. This is one of the most important features, as we will see later. The time available to perform the turnaround, which is basically how much time do we have to unload the aircraft, unload it again for the next flight. So the difference between the expected of block time and the estimated time of arrival or the actual time of arrival. Okay. Another feature that is very important is the air traffic flow management delay that is assigned to the flight, if any. So if the flight is regulated, we will see that in many cases, it receives a slot improvement. And this means that the aircraft actually takes off before what was predicted by the ETFMS. So this feature is also very important. We also included some features related to congestion at the airport, like the number of operations that are planned near the expected takeoff time, the estimated takeoff time. So how many departures and arrivals. Also, the delay state of the airport, like the distribution of delays in the last hour at the departure airport. This means, for instance, how many aircraft departed with a delay of between 10 and 20 minutes, or 20 and 30 minutes, so the distribution. Obviously, we also included some weather features like temperature, visibility, the cloud coverage, etc. And basic calendar features like the hour of the day of the week, or the month of the year. This is just a short list of the features. You can find all the features in the paper that I will show you later. We tried two models, two very different models. The first model is gradient boosted decision tree. That is basically an ensemble of weak decision trees that together perform quite well. And we use the implementation of Microsoft that is called LightGVM. Okay. The LightGVM model makes a prediction for each individual message. So remember that for a given flight, we may receive more than one message. We may receive the initial flight plan, several periodic transmissions, and other kinds of message. So the LightGVM makes a prediction for each individual message, disregarding all the previous messages sent by that flight. Okay? But we thought that maybe if the prediction of the ETFMS is very stable from the initial flight plan, so during all the messages, the ETOT is similar, we could rely more on the prediction of the ETFMS. This is why we implemented another model that is a recurrent neural network. And the recurrent neural network makes a prediction not only based on the last available information of that flight, so the last message sent by that flight, but using all previous messages. So the sequence of messages sent by that flight from the initial flight plan to the moment of making the prediction. We test both models, and honestly, the performance was very, very, very similar. And this is why I am only going to explain the results of the LightGVM. because at the end the results were almost identical. Okay. And the advantage of the light GVM is that the model is not really a black box. In light GVM, you can understand what the model is doing, why it is taking the decisions, and which features take more importance when making the decision. Okay. This is why I will focus on the light GVM results. We train both models with the same dataset that includes flights crossing the MOAC airspace from January 2016 to December 2018. And we order the flights by date, and we use the first 70% of the data to train both algorithms, i.e. both models. The next 10% to find the best hyperparameters, so fine-tune the hyperparameters of the models. And the last 20% for testing the performance of the models in data that the models have never seen before. In the left table, you can see the performance of the light GVM and the ETFMS aggregated for all the messages in this time period from the test set only. And we can see that the mean absolute error of the takeoff time prediction of the ETFMS is around 14 minutes, and that we are able to reduce to 10 minutes and 40 seconds by using machine learning. So this is a benefit of around 25%. Okay. Interestingly, we also decrease the error in the 3 quartiles and in the standard deviation, meaning that our predictions are more stable, are more reliable. Okay. Remember that this table shows the aggregated results for all the messages, regardless of the look-ahead time of the prediction. But it's also interesting to analyze the results as a function of the time to the takeoff. And this is what you can see in the right table. Okay. You can see the results divided by time to take off, so the look-ahead time of the prediction. And we can see that most of the benefit in relative terms is when we make predictions between 1 hour and 6 hours before takeoff. 1 hour before takeoff, the relative benefit is quite small, is around 20%, because the prediction of the current system is already very good. It's between, 6 and 10 minutes. But if we move to 1 hour, 2 hours, 6 hours, the benefit is around 30%, up to 31%, 6 hours before the flight. Okay, and this in the bottom of the slide you can find the title of the paper where you can check all these results, the features, the models, etc. So now, as I said before, the advantage of the light GVM is that you can check the importance of the different features. You can understand what the model is doing. The y-axis shows the top 10 most important features according to the model. Okay, ordered by importance from top to bottom. So the most important is the available turnaround time, as I said before. In the x-axis, you can see the importance of this feature. Okay, and each dot, I know that is difficult to appreciate because of the resolution of the image, but there are several dots. Each dot is an example of the test set. So if the color is blue, it means that for that particular example, the value of the corresponding feature was low. And if it's red, it means that the value of the corresponding feature was very high. Okay. And the impact of the model, which is the x-axis, is how the model used that feature in the prediction. Let's see an example. Let's analyze the available turnaround time. We can see that when the value is very small, so very blue, the impact of this feature is positive, is around 40, 50, 30. This means that the model uses this feature to predict that the aircraft will be 30, 40, 50 minutes late if compared to the prediction of the ETFMS. This makes sense because if the available turnaround time is very small, very low, you will probably not make it, and you will probably be delayed, and you will probably depart later than what is expected according to the ETFMS. Okay. If we analyze the ATFM delay, which is the 5th feature according to this graph, we can see that when it's very high, very red, the model uses this feature to predict an earlier departure, meaning that the model knows that in most of the cases, you will receive a slot improvement and you will depart earlier than what is expected according to the ETFMS. We could also analyze the importance of the different features as a function of the value. I will only show the importance of the available turnaround time. You can see that this is the left figure. You can see that when this feature is very small, that is the the X. No, when this feature is higher than 1 hour, that is the X-axis. The importance of this feature, that is the Y-axis, is 0. So if you have a available turnaround time higher than 1 hour, there is no issue. You will probably depart on time. When this feature starts decreasing, so it's lower than 1 hour, the importance of this feature starts to increase very sharply, meaning that you will probably depart later than what is expected according to the ETFMS. Okay, and each point again is an example of the test set, and we could analyze all the features, but this will take a lot of time. All the analysis is again in the paper that you can download in the SESAR website. So I presented a model that, well, two models in reality, because both models perform very similarly, that is able to improve the takeoff time predictions by around 30% using only data available in the ETFMS. We believe that we could improve even more the performance of the models if we were able to use data specific from airlines, like the crew schedules, catering status, boarding status, and other kinds of data. I must say that we try to use only ETFMS data intentionally to make a more easy deployment in real life. But these are just future-ward directions to improve the performance of the models. We could also improve the performance of the model, of course, using data from the airports, like the utilization of the gates or the departures and arrival sequence. And also to use some features that were able to capture network effects, because now we only use the delay of the previous flight and also the available turnaround time to capture this kind of network effects. But we believe that other features could help to improve the performance of the model. And that's all for this presentation, and I will be very happy to answer questions.
Thank you very much, Ramon. That concludes the presentations. Meanwhile, we have plenty of questions coming in. I'm starting to get a bit of a challenge in moderating it all, but I would indeed invite all the speakers to come on stage now so that we can have a more open discussion about all the questions. I'm happy, by the way, to the audience that with all the questions that were coming in, it means that you're engaged, that you're interested. Actually, some of those questions are very detailed and technical, where we definitely need speakers to answer them, and that makes me clear that I'm not the expert on this topic either. So let's start at the beginning with the question on GDPR. So data privacy, personal data protection, reliability, data ownership. I think it's a question that is at least for Ricardo, but maybe Anita, you also want to say something about that from the controller and the pilot perspective in the projects on the voice recognition.
Mm-hmm. Yeah, it was a double question. Actually, it was asking first about data ownership, second about personal data protection. So I tried to reply very briefly in the chat, but I'll expand on this. On data ownership, this is a very relevant point. We have different situations here. In the case I presented in my slides, the mobile phone data, this is data owned by a third party, which is collected originally for a different purpose. So it's a real issue. We need to find the right value chain, the right business model, so that the owners of this data are willing to share them under, let's say, fair and safe conditions, and this data can be exploited for, in this case, for transportation planning. We have other examples in the project that I didn't address in the presentation, in which the data is owned by the end user of the analysis, like this happens very often with smart car data, I don't know, data such as Oyster car data in London, for example, which can be used to analyze mobility patterns in the public transportation system. In this case, the public transport authority is usually the owner of the data, or it can happen the same with airport owned data. In these cases, it is easier because, okay, these agents are willing to share the data because they are the direct beneficiaries of the analysis. In the case of third parties, like mobile phone networks, we need to find, as I said before, the right value chain or the right business model. Second question is about GDPR. Basically, we do three things in most cases with most mobile operators, and this is the general procedure that we have got approved by several data protection authorities, and we believe is the right way to go. First, the data is originally pseudonymized. That's the technical term. It's not fully anonymized, it's pseudonymized, which means that you apply a sort of hash function or encryption function to the personally identifiable information. In the case of the mobile data, for example, this can be the IMSI code or the mobile phone number or whatever. So this is encrypted. Then the second measure is that we typically process this data within the facilities of the data owner, in this case, the mobile operator. So they set up a secure environment and we install our software there, but we never take disaggregated data outside their facilities. And the third measure is applying aggregation criteria. We produce origin destination matrices or aggregated travel time distributions with a level of aggregation that renders the data fully anonymous, or that, in other words, that prevents any risk of re-identification. So in let's say at a very high level, these are the main measures to ensure that there is no disclosure of personal information.
So Ricardo, I remember that when we launched that project a long time ago, that we had an ethics review, which is how it works on Horizon 2020. And the issue of GDPR was a big issue at the time, and the anonymization. If you do the anonymization of personal data, can you still do any correlation between different data sources, or is that causing a big problem?
Yeah, that's why we produce this aggregated data. Sorry, because even if you anonymize the individual registers by hashing the IMSI code or whatever, you could still, let's say, blend this information or these individual trajectories with other data and re-identify somebody. So this is something we explicitly avoid, or we explicitly forbid, let's say, in the projects in which we work with this data. We do everything at an aggregated level, in a more, so to say, statistical approach. We have aggregated patterns that come from mobile phone data, or aggregated shopping patterns from credit card data, or aggregated public transport usage patterns from smart card data. But we never try to, let's say, match individual identifiers. What we do is creating, or the workaround is creating synthetic populations, or populations of artificial agents that at the aggregated level match the aggregated patterns we observe in different data sources. And we rely on the assumption that this will be representative of the behavior of the real population, but we don't create an individual by matching the identifier of the mobile phone with the identifier of a boarding pass with the identifier of a smart card data, because that would enter into privacy issues, and it's explicitly forbidden by GDPR. So the workaround is to do this on a statistical or based on a statistical approach. We use this synthetic population approach.
Okay, thank you very much, Ricardo. Anita, how was that for the controllers? Were they cooperative? Were they willing to have their voice recorded? Are you having any problems with the pilots in the future projects?
I have to say that our controllers are quite are willing to cooperate on the project if they see that something useful for them, and this is the case. So at the first time Mallorca, it was a little bit hard to get controllers on board because they couldn't see anything. We just asked them that they will be recorded. But we found several controllers, and when they saw results from Mallorca, controllers for PJ 1604, it was not any problem. So I would say, and it's a pleasure for me to work on projects that really bring something to the controllers. They can support them.
I was also wondering, in that same context, we had in the previous webinar some discussions on explainability. on trust, safety is related to trust as well. Did you experience with the air traffic controllers that their gradual increase of understanding of how the machine learning works, that it leads to both an increased trust that it actually works, and therefore also more cooperative attitude, more willingness to be conforming with the phraseology and things like that? Did you see any change in behavior there?
I was not present to PG 1604 directly or personally, but as I said, there was a clear observation that if you see results from first run and second run with the same controller, there was the improvement. Even the second run was with higher workload. So it's clearly obvious, and maybe if Hartmut wants to add something to it, but to me it's absolutely visible, and controller understand how the system can support if they stick to the phraseology and they improve their pronunciation.
Hartmut, is there anything you want to add on that?
Yeah, maybe I think it's not the correct approach that we adapt the controllers to the speech recognizer. We have to do the other approach. Yeah, we need to adapt the speech recognizer to the controllers, and even to the more experienced controllers who invent a little bit different phraseology. I think there are good reasons why they are using that.
So, since we're on this topic, there's another project here which is also working with controllers, or actually the controllers are working with the tools that are being developed in Maastricht upper area. Derek, I guess the same question for you. What are your observations on how the controllers perceive the advice on this machine learning tool?
Well, actually, yeah, I would agree with Annette. As long as what they see makes sense, there will be no problem there. They're actually very eager to help and to explain what they do. The fact that the machine learning is complex or anything, it doesn't matter. What really matters is the end result. If it really, I don't know, if a tool creates too much false positive, false alarm, then it loses usability. Maybe not trust, but it loses usability, so they reject it. And then once you have good enough results, then they embrace it if it helps them in their day-to-day life.
Yeah. Okay. Let's move on to the Eurocontrol application on the takeoff predictions. I see a bit of a technical question here. Ramon, I think you already answered it on the systematic errors, which you were referring to. Can you give some examples of what you mean there?
Yeah, by systematic errors, I mean prediction errors of the current system that can be explained by selecting the right features. So, for instance, this is what I answer here. When there is a lot of congestion at a given airport, the current prediction, the ETFMS, may be too optimistic. And in most of the cases, due to the large congestion, the aircraft departs late. And this is a systematic error that you can learn from the data. This is the concept of systematic.
Okay.
Imagine, because for that specific question, we were speaking with several pilots to try to understand the reasons behind the delays. Because there is a hunch, there is something that says a lot of the delays happen randomly. And when they happen randomly, there is nothing that you can learn from. Imagine they had a lot of stories about people getting sick on the plane just before they depart, and they had to postpone the flight for 30 minutes. This is completely random, and when you have randomness, you will not be able to predict it. So that's why Ramon has been trying to identify which are the delays that are systematic. You will not have 100% prediction of the delays, but at least the part that is systematic, if you can reduce the error there, this will be a significant gain already.
So if I try to connect this to the previous webinar where Professor Jesus Garcia presented on the different waves on artificial intelligence. So he explained the difference between expert systems, where basically the developer predefines the features, versus deep neural learning, where the system abstracts itself what the features are. Where would you say that the Eurocontrol application is? In which wave of this artificial intelligence development?
Well, at the end, the features are selected by us, by the data scientists. But then there is a post-process to analyze which features are really important and which features are not adding any benefit to the model. And it's true that the model that I presented here includes all the features that we used. But later on, we make a selection of the most important, and we have now a second version with SEDIC with a low set of features. Now, for instance, we do not include some of the weather features because the benefit that they add is very small compared to the complexity of taking the data, processing the data, merging the data. But at the end, yeah, I think the features are selected by the data scientists, and then you need to check which are important and which not.
Okay. A more general question on the usage of this data. So far, from your presentation, I understand that it's in particular a Maastricht upper area which takes advantage of this improved predictions. Is it just the MUAC, or are there any other ANSPs that are interested in these results or are using it actually?
In fact, in NM, in Eurocontrol in Brussels, they are also developing a similar model, and we work together. So we share our experiences and results. I don't know really the status right now, but I know that they are actively working on this. So, yeah.
Okay. I guess the same question is for on the speech recognition for Hartmut, I guess. I saw on the slide that you were standardizing, so the ontology with, if I remember well, 15 different stakeholders or different countries. I'm actually not sure I remember that well. How is the uptake of speech recognition in an operational environment at this moment?
What do you mean with uptake? We agreed with 22 partners from 15 countries concerning rules or how we want to agree on the semantics, so that we can, and everybody sees the benefits of having standards, because then you can exchange data, then you can develop different building blocks of speech recognition, for example, for just for text, for speech to text, and for command prediction, and for extracting the semantics, or that are the best from each partner can be integrated.
Okay. Before I go to, I think we're about to finish. I have one last question related to speech recognition. But before I go there, is there any of the speakers that triggered by the questions that were raised wants to clarify anything?
So if there are questions still, or you have my email, contact me.
Okay. Then the last question, it's again related to speech recognition. It's a very generic question. I saw that you answered it already, Hartmut. And it is about why do we need speech recognition if we go to data link? No.
Yeah,
hard question, I guess.
When we are going to data link, maybe in the meantime, until the next 80 years, maybe we are still needing speech recognition. I think the most efficient conversation, how humans are talking, is still speech. We are now doing it via speech. Why I'm not typing it? Yeah, because we can express more with words. But I think as soon as we have something in the ops room, it just helps us. Yeah, why not integrating speech recognition with data link? The controller still talks to the pilot, but why not in parallel sending that out? Yeah, then he has two communication channels. If he's not understanding, maybe he gets the result of the speech recognizer on board.
Yeah. So I think I do support that. There is also a good reason that we're happy with these projects. Even though data link is something that we're definitely also pushing as well, we have future webinars on trajectory-based operations and how we're moving forward with complex clearances, getting a tighter integration between aircraft and ground systems through data link. But nevertheless, as we see today, data link is still relatively has relatively limited applications. Some of that is due to just technical issues on the performance of data link, which there is work going on the ELSA study, for example. But there is definitely, as far as we see, good justification for keeping the work on speech recognition as well. If there are no other remarks from any of the speakers, are there? Anyone last chance? Then I'll finish off here. It's 11:15. We overrun by 15 minutes, which is better than yesterday when we overrun by 30 minutes. I want to thank the audience for having been listening in, coming back to our 2 seminars. Hoping to see you back at the next webinars in September again. Thank you very much, speakers, for your contributions.
Thank you.
Goodbye, everyone.
Thank you, everybody. Have a nice weekend.
Bye-bye.